This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
All right, everyone, let's get started. This is EE380, and today's speaker is Alan Huang from Terabit. He has a bachelor's and master's in electrical engineering from Cornell and a PhD from Stanford. He's going to be talking to us about Terabit. Before he was at Terabit, he was at Bell Labs for many years, and one of his key accomplishments there was being the co-inventor for the Batcher-Banyan packet switching networks. He has over 30 patents, and now he's started a new company called Terabit, and he's working on an ultrafast optical digital technology. You might think that this talk is going to be all about physics and it will be confusing to the computer science folks, but actually there's a lot of computer architecture involved, and it's more computer architecture than physics. So that's what he'll be talking about today. Please welcome Alan Huang.
Thank you for having me. It'll be great. You're not going to force me to sit down. Hold on, wait a second. Let me change the. This is sort of hometown advantage. I'll be talking about. I had a joke. I went to grad school with Dennis, and if he was here, I'd have shamed him a little. It turns out our careers went two different ways. I got to go off to New Jersey and learn more than I ever wanted to know about telephones, but he was stuck here in Silicon Valley, and he had to sit through all those meetings in hot tubs, you know. But, you know, some people are luckier than others, what can I say? All right, I'll be talking about very fast digital circuits. And what I'll do is I'll start off with, this is an overview. I'll be giving some background of where I'm coming from in terms of how to do very fast digital circuits, my electronic background, and also some things of how to do it with optics. I will try to explain in this talk, hopefully it won't be too confusing. I'm going to try to say what and how, in other words, what the idea is and how I came up with it. Then I'm going to go and talk about why this is important down here, and then I'll sort of like close off with a historical perspective. Okay, next slide, background. All right, this has to do with my first project here after Stanford. What?
Can we turn some lights down? Because contrast on that could be a little better if we got rid of some of the lights.
Yeah, okay, this was a first project I worked on after I finished Stanford. And this is basically a Batcher-Banyan. It consists of a lot of small state machines. It was electronic. It has sort of Stanford roots. It was basically, I took the course Sorting and Searching from Knuth, and my partner, Scott Kenauer, studied with Harold Stone and did the perfect shuffle. We realized that basically routing is sort of sorting backwards. We also figured out that if you sort of come out in sorted order and you go into a Banyan network, you don't block. And so the point here on this particular view graph that I want to bring up for this talk has to do with the fact of this consists of many little state machines, and I don't show here, but the feedback was a lot of long shift registers. And so that was how we're holding our state or the packets in this network. This shows the TTL version. It was 100 megabits, 32 channels in 1982. The TTL version is shown there, and you can't see there's a VLSI version, which was, we tested it up to 20 megabits per second on 32 ports. And that will come up later, too. Then this is my optics point of view. This was basically, on the top there was 3 optical benches trying to control 48 gates. And this was in 1984. About a year later, we got it down to about 1 square foot for about 48 gates. We then went to put 4 of these together, and this happened to be a state machine also. It's a pipeline state machine. It's very simple-minded. This was sort of using some of the same technology to do a circuit switch, and that happened another year later. That was 1987. That was showing, most of those projects were mainly the using a parallelism of optics to move a lot of signals around. We had another program going on that most people didn't know. It had to do with going to do ultrafast logic. This was a chart produced by Peter Smith, and it shows down here on the bottom axis, if I can get the, okay, on the bottom axis is basically goes from 1 to terahertz. From here upwards on this axis, it has to do with optical power. This shows various technologies and how much energy. There's the semiconductor devices up there. There's Josephson junctions there. And there's certain limits where you can't get to. In other words, this is thermal limit, a quantum limit. There's a thermal transfer limit. If this was in a semiconductor, you'd melt it. What we're going for is the optical transparent devices around the terahertz. This is what the device looks like. It's basically a Sagnac interferometer. We did it in fiber and polarization preserving fiber. The way it works, if I can ever get a, here we go. You basically have a fiber interferometer right here. You have a 50-50 splitter. One part goes around clockwise and another part goes around counterclockwise, and you do this on one axis of polarization of the fiber. Normally what would happen would be the light would come back, it would have constructive interference right here, and would continue out this way. So it would act like a mirror. You'd come in here, go through this, and you'd come out here. What is changed, though, is if you inject a pulse at exactly the same time on the second axis of polarization, what happens then is you experience an all-optical Kerr effect. It's also called cross-phase modulation. It's a basically, the light E field of one optical pulse effects, or both of them together, affect the index of refraction and actually slows it down, or gets it's basically a pi phase shift. So what will happen is, come on, back pointer. Okay, instead of getting coherent interference at this point, you'll get coherent interference here and destructive interference here. So what will happen is the light will seem to emerge out this port down at the bottom, output X. So in one case, you come out here. It's like a single pole double throw switch. So one pole, you come out here. The other time, you come out on the other thing, depending on whether you have light coming in. So it is literally light controlling light, indirectly, but that's how it works. We did various experiments. We did one experiment where we just hooked it up in a loop, and we got 2.5 gigabit loop, and it just went around and around and around for more than 20 minutes. We did this other experiment here. It ends up, because there's two different axes of polarization, one of the troubles of doing ultra-high-speed logic is you usually have to have both inputs at the gate at the same time, and that's kind of difficult to do. So in this gate, it has an unusual feature in that you have the slow axis of propagation and the fast axis of polarization. So you first send in the first pulse on the slow axis, and then you send the stuff on this input on your fast axis, and they'll slowly pass through each other, and you'll still get the same effect. And so we call this jitter tolerance. And we could sort of engineer it to be sort of plus or minus up to 200 picoseconds. This is the experiment up here on the top that sort of caused us a lot of trouble. In semiconductors, you could basically time how fast your process is by sort of like cross-coupling two gates and seeing what the free oscillator time is. Well, I suggested to some of the researchers in my group at that time, we should do the same thing for this device to see how fast the switch could switch. And what we did was we took a length of optical fiber, put a mirror at one end, an optical amplifier in the middle, and we put one of these switches down at the end. And on the output, we put an optical autocorrelator to see when it would go. And I remember the two researchers that came back with the results. One was Paul French and Hercules Alferopoulos. And they asked, like, Alan, it comes out to 1.2 terabits. Do you really want to publish this? This is going to get us into a lot of trouble. And so I thought about it for a while, and I said, okay, go back, run the experiment again, and if you get the same value, then publish it. All right, they went back, they got it. We went through the complete clearance process. A month later, we sent it in, and a few weeks later, I get this call from my manager, and he freaks out. and he wanted us to withdraw this paper. And he demanded to see the actual output. It was a big hassle. He just freaked out. And what happened was the cure for it, he wanted us to withdraw the article. But it turned out that I said, well, we can ultimately just redo the experiment. I can show you the results. And when I showed him the experimental results, he just said, okay, fine, publish it. But this is sort of what helped me earn the reputation of being a wild man, being, not only a danger to myself, but to Bell Labs and the science in general. And so that's kind of a famous experiment right there. Then later on, we went and we gathered various transfer functions of this. I put it together of this particular gate. And I'll talk about that later. What has happened after basically that was done almost 15 years ago? What has happened since? What has happened since is basically we're at 2.5 gigabits down here. Later on, NTT, or British Telecom, managed to push it up to 160 gigabits. Then it was taken over by NTT, and NTT managed to push it up to 1.28 terabits. And this is from the same gate, where it's a simple multiplexer, demultiplexer, and we did it over, or they did it over 70 kilometers. What I think the moral about this is they shoot the messenger, whether the messenger is right or wrong. Okay, the next point here is what and how. Okay, what have I been up to in the last probably 10 years? All right. What had happened was when I was here at Stanford, one of the key points was how to do Mutant Conway. This was how to do VLSI systems. And in those times, what happens, the nerds carried around a pen just like this. It's 4 colors. We had different ways of writing these different circuits. And what is taught in Mutant Conway is you first start at the device level, then you go to the state machine, and then you go to the application level. And in retrospect, this turned out to be really wise advice, because what it does is it decouples the physics from the applications. And one of the troubles of optical computing for a long time has been that they were connected. In other words, the systems people would drive the device people crazy, and the device people would drive the systems people crazy. And so this is sort of establishing an intermediate API that would keep the system stable. So I decided to pursue the same thing, and this is the device I was using, the coupler that I talked about before. Okay, now I'm going to push up to the state level, how you can use state machines. What I literally took was, this is a diagram from Mutant Conway. And the first part is basically the AND plane, the other part is the OR plane, and there's a register down here for re-registering the outputs. And this is how you do it in, I think, NOR logic. And I basically took the optical logic gates and put them in exactly the same place. And so here you've got basically the AND plane. Over here is the OR plane, a wired OR plane, and these are the registers for redoing the signal. The first problem is this is just too many optical logic gates. And there would be too much loss, it would be very expensive, etc. What happened was, I worked with a guy named Scott Kenauer, and I'll explain to you why, the Darth Vader icon later. He's also a Stanford grad. What happened was he had this conjecture that when you're doing high-speed circuits, both your inputs of the gate should be running at close to the clock rate. Otherwise, you're not fully utilizing the gate. In other words, there's a simpler circuit that you just have to find that would sort of use everything up to its duty cycle. And when I looked at this, I said, okay, here the columns are being driven by my inputs, and they can probably go at 100 gigabits, but my midterms coming in from the side on the rows are just sort of basically DC, or not really going very fast. And so what I realized was that if you put the midterm lines, the row lines, on different wavelengths, you could basically collapse the whole structure. And this is the structure just collapsed down. Up at the top here, okay, here are the Sagnac intergates. This is the bypass. So you either go through the gate or you bypass. These are my sort of prime implicants, my inputs coming in. These are staggered delays up on the top. Here's the wired OR planes that come back down, and they go into a register where they gate a clock and it comes back, and some of them are fed back again. But you'll notice that this is still kind of quite a few gates. And one of the problems happens to be that I'm using a dual-railed logic system. I'm using an input and its complement. Well, in a strange thing that happened here, when I was at Cornell, I had a professor who taught digital switching theory named Professor Torng. And he basically, what I thought, wasted our time for the first 3 weeks of the course by teaching us how to do circuits out of relays. And I was like, come on, give me a break. I want to do the TTL stuff. I don't want to deal with these electronic relays. I'm not going to be controlling elevators. And what happened was, well, I thought not very good thoughts about him. It turns out that mathematics was necessary to basically reduce the number of variables and inputs that I needed. And when I actually hunted him down on the internet, and I apologized to him recently. He was now living in Walnut Creek. And what was kind of funny, he told me basically he had this idea because he was a postdoc at Bell Labs, and they gave him all these old relay computers that no one could figure out how they worked. And so he had to try to find a way of bridging from that mathematics to the newer mathematics. This circuit is what I fondly refer to as my most likely to have come from a flying saucer circuit. And you know, if I don't tell you what the inputs are or something, I sort of give it to you in the parts, you wonder, what in the world is going on here? I've sort of wondered, I started realizing that if I sort of gave this to a VC, and if I was actually a person from a flying saucer, I'd probably get funded. If I only claimed that I was abducted by them, then it might be a little harder time. But all right, this goes about the tools, how to build these systems or how to sort of engineer these systems. And I realized this thing was sort of plumbing. I broke down the problem into plumbing, and it was getting the right amount of light at the right place at the right time. The second one was sort of timing, because I had to get the whole things. But you'll see that I didn't quite get the timing right. In other words, that was a hard thing to deal with. And this is where it ties in with computer architecture. So what I found is this is a cute little trick if you ever have to sort of generate a lot of equations. You sort of make a little Excel little kernel here, and then you just cut and paste them. And according to your system, you can build up the system. It gave me how many dB down I was, how many nanoseconds or picoseconds it took me to get through, but it still didn't give me the feel of it actually working. I then went to another thing of sort of writing a Perl script on the computer to try to simulate the state machines at a higher level. But here I was, I'll show you some of these machines later, but I was sort of stuck at the high level. I got something working, and the bottom level I didn't quite get what I needed. And I remember showing to some friends here from grad school, which was kind of amusing. I showed the simulation to one friend, and she said, Alan, this really dates you, because I animated by sort of using a fixed size frame. You'll see this later. I showed it to some other friends from grad school, and I think they felt sorry for me. And about a couple of months later, they ended up giving me a 64-bit Athlon with PSpice on it, so I can actually do the real job rather than trying to use Excel and Perl. So what happened here with the PSpice model? It took me about a year, but I ended up building up, this is sort of like all the equations for one gate. And what was cute about PSpice, it's completely hierarchical, so you can push all the way down. And when I push all the way down, I actually pasted the spec sheet of the component that I modeled. And so you just sort of push all the way up, and then I sort of connected all these things together. But this shows you how many equations it took to just model even just one simple gate. I got all the back reflections, I got the cross-coupling between the polarization things, etc. In fact, I could say that this is a simplification because I actually did it forward and backwards, so it's twice as many equations. But it turns out the back reflections weren't really significant. So what happened after I modeled this? First thing I did, I tried to explain in one of these memory loop experiments. Put it into a memory loop and see what happens. And sure enough, if I got the right threshold, the stuff would actually store. There's a funny story about this particular thing, because I had spent years wanting to have this simulation program called either OptiWave or RSoft. These things were for simulating optical systems. It was like, oh, if I could only get my hands on these things, I could actually do it. It ends up that both these programs didn't have one thing. It didn't have a delay line. It didn't have something to do delays. And it ends up that The only way to get that is really from SPICE, and they have ideal transmission lines, so I can specify how many nanoseconds or how many picoseconds worth of delay, and it ends up that delays are basically my memory element. All right, so if you don't get it right, or you can sort of like adjust a different energy, how much light you're coming in. If you don't get it right, then you'll see the stuff will just decay down, etc. What happened was I got a little more ambitious after that. I actually built circuits. I actually built a circuit here for a divide by 4 circuit. I interlaced it by a factor of 4, and so there's sort of like 4 of these state machines running together. I superimposed the 2 bits, 2 state bits, and so you can sort of see that it sort of counts by 4. There's 4 of them interleaved there. And what I wanted to point out about this particular simulation is they're all analog components up there. There's no digital component. All right? There's no gate hidden in there. It's all sort of analog equations. All right. I had this problem still. I had plumbing on one hand and juggling on the other hand, and I couldn't put them both together. In other words, I was writing this patent, and it was like 20 pages worth of formulas, and they basically didn't give you any feeling for what was going on. You couldn't tell what was, this had to be bigger than this, but this had to be smaller than this, and when the moon was blue, you had to do this, and it was just, I said, I've got to find some way of sort of like organizing this. And the answer came to me, it was about a year ago, and it was from the San Francisco Chronicle, the Sunday Chronicle. I saw this on the top. It was basically a hydraulical map of the hydrostatic head between Yosemite and San Francisco. And it all had to do with whether we should try to drain Hetchy Hetchy. Hetchy Hetchy is the valley that's next to Yosemite that's become a reservoir. And so they show this map, and it starts off at 900 feet and goes all the way down to basically San Francisco. And I realized from that, or any techie looking at this realizes, instead of storing the money or the water at 900 feet, you could just store it anywhere in between. So you could literally drain the Hetchy Hetchy, and it wouldn't really disturb the system. All right. What that reminded me of was a very famous graph from Menard, and it was Napoleon's Moscow campaign. And it basically shows here, he had his number of troops here. This was time axis, and also between Paris and Moscow. So you can see how he was having troubles. He also plotted the temperature shift. He plotted various other things. And so it gave me an idea that you can basically put your time axis on one area, or your distance axis, and on the other axis you can sort of have a power. And so that led to this diagram here. This is, I basically did a cross-section of the optical, my flying saucer circuit, sort of part by part, all the way through as a function of time. And so on one axis was the how much optical power, that's like 1 watt. I show various inputs here coming at different times. I show the decrease in optical levels, and if I sort of put 1 watt here, you'll see that I'll have so much of a drift down at this point. If I put another input here, at this time, I'll get so much of a decrease. The current, the curve will shift down. I'll come to this point, come over here, I go to an optical amplifier. Now that output basically couples to this input. I have a certain optical clock coming in here. Basically, if I have 1 watt of optical power here, I will only get this much of a sort of decrease in my amplitude. And if I wait exactly so many cycles between here and feed this back to this input, then everything will work out right. It'll be a 32 interlaced. This circuit happens to be for the state machine. So now is a way sort of how to choreograph the power or the plumbing and the juggling. Now to the application level. First thing is people saying, okay, how are you going to interface electronics, the slow speed of electronics, with the faster speed of optics? And it turns out this comes to be a multi-threading trick. I thought that was kind of interesting. Basically what you can do here is if you get a state machine, and instead of having 1 bit of state here, I know, I can't see one point. Okay, if you have a state machine here and you basically have 4 bits of state in your feedback loop, what you'll see that you can do a 4-way interlace. And they'll show right here. Yeah, that would be, I don't know why the mouse always disappears. All right, and so what happens is basically you can sort of view these as slower electronic channels that get interlaced, and so you can use a faster optical state machine. And so all the stuff I'll be talking about, all the state machines I've been working on, are basically sort of interlaced. And I was amused at 1.2 terabits, if I interlaced it 19 million times, I could handle DS zeros. That's a bit of stupid telephone stuff. All right. What occurred to me was how to do an optical memory. That's one of the things that have been missing in sort of optical computing. And what occurred to me was instead of doing a random access memory, I could just do sort of a FIFO queue. And then it occurred to me that you can sort of do a FIFO queue in a distributed manner, little pieces. And so this is sort of like the layout for packet FIFO. And I remember sort of like thinking about it, and I said, okay, now I had to figure out the algorithm for how to do this FIFO for the state machine. And I looked in all my books, my old Mutant Conway and some other books from the early days of VLSI, and I couldn't find the circuit. And I said, oh God, I'm gonna have to do it again, but it can't be that hard. You know, I have to do it from scratch. And then it occurred to me, like, maybe I did do it. And I look up in my second patent at Bell Labs, and it was distributed prioritized processor. So this was more than just the senior moment here. What happened, though, when you look at the state machine, you basically have storage loops of a packet coming through here. And one of the complications is you have different size packets, and you don't want to switch over to the next storage unit. It's like a bucket brigade. You don't want to start, transferring before the halfway in the packet. Otherwise, you're sort of like, it's like The Fly, the science fiction thing. Get reassembled wrong at the other end. So I was really worried about that. I got this all to work. And a couple of weeks later, I woke up and I was dreaming about my goldfish. I have never dreamed about my goldfish. I had goldfish, I think, when I was in 3rd grade. I think it's one of those things that Dr. Spock tells parents to do, so they're socialized. So I had these 2 goldfish. And the trouble was you had to sort of replace the water every week. Right? So I had this little net, and I would go there trying to catch these goldfish. I would catch the goldfish, put them in a little cup, pour off the water, and then fill it up with water, and then catch the goldfish and put them back in. And it traumatized me as well as the goldfish. All right? And this was sort of like one of those memories from growing up. It wasn't until after college I was visiting a friend who kept a lot of tropical fish. And I watched him change his water. And he just takes his aquarium and pours out his goldfish into a cup, pours out the rest of the water, fills up the water, and then pours the goldfish back in. He doesn't catch them at all. So what I realized here, how this applies to this thing, is if both storage loops are exactly the same length, and I can be assured of that I completely empty the storage loop or transfer it, it doesn't matter where I start. Everything will be reassembled perfectly. It only adds to the condition is you have to have both of them exactly equal, and you have to make sure you empty the thing completely. And so that's gratis of goldfish. All right, this one. Let's see if I can do this. All right, here. First thing I will show you is how to do some of the simple state machines for doing like a FIFO. So if you can imagine, this first one here is, these are various storage loops. And basically my input will be coming in from the top. These things are in bypass mode now because they're empty. And you'll see the packets accumulate down here at the bottom. So I'm beginning with a B. It's coming down here. It gets into the storage loop, and you'll see it's our VEGIN. It's my beginning of header. There's an address, 0, and then there's the data, and then I have another field, and then I have end. And you'll see that another packet's coming down here, and this packet will be frozen into the bottom loop, whereas the next packet is sort of like being captured by this loop. They end up going around and around as their circular storage things. And what will happen now is if another packet comes in, it'll fill up this guy, etc. If I touch the right input, they start draining out. All right, so that's how to do like a FIFO in very simple state machines. And I want to show you the next one down here is, this is a hub. This is basically, I have 4 circular registers as my input, and the hub basically I have to select which output port. I think I have to start this again, in fact. All right. Come on. How come I don't get a prompt here? I logged out, damn it. Excuse me. Well, you're going to have to see this later. All right, back to my talk. All right. Slideshow. All right, this is another example of sort of how to do the circuits, because people are really sensitive, like how do you go from electronics up to optics? And this is a very unusual multiplexer and demultiplexer, and it uses some unusual aspects of optics. Basically, I have many different electronic inputs. They're each modulating a different optical carrier. I come into a Sagnac, which acts as like a shutter, and basically captures like a rainbow of various inputs. I then put it through an optical delay lines that are sensitive to the wavelengths. So I basically stagger the different bits. I then basically use it to drive another Sagnac, which basically will reclock it and change it to a different wavelength coming out. All right, so that's my mux going out. And this is my demux. I come in with my data stream here. I basically make clones of it. I have different wavelengths here. And so this input data gets basically duplicated on different wavelengths. I then come here and inversely shift the different wavelengths, and then I use this Sagnac to sample out and cut it out. I then basically shovel the different wavelengths to different receivers. And so that is basically a different way of doing a demultiplexer. What is unusual about this particular circuit is most multiplexers have, they're linear multiplexers. For n input you need n switches. And for sort of like a demultiplexer, it's sort of like it works the opposite way. You could also do it with a sort of a tree circuit where you have 2 to the n minus 1 type of switches coming down. What's unusual about this circuit, it uses 2 gates, sort of independent of the number of inputs. And sort of 2 gates here, independent of the number of outputs. This patent has just been allowed. All right, why do this? First thing, I want to show you that these things are smart. And it's the difference before, people have had logic gates for some time. What the realization is, by adding a little bit of optical delay, you can use this delay as memory, and as a result, you can get logic plus memory. And so the machines can be smarter. I wouldn't count on these machines doing your income tax anytime soon, but it's smart enough to move a packet around. Yeah. All right. The next thing, why, and it ends up to be speed. This shows that it's greater than a terabit. All right. Electronics probably will be maxed out about 50 gigabits per second. Since this optics is going that, we're talking about a factor of 25 here. All right. This one, why? It ends up that Sagnac gate has a very unusual property. It's a function of the E field rather than, and so what happens is it uses the same amount of power no matter how fast you're going. If it's, it'll take 1 optical watt if you're running like at 10 hertz or at 100 hertz, all right? And the rest of the circuits are basically passive circuits that just sort of dissipate power. Their optical amplifier, it takes the same amount of optical power no matter how many bits you're pushing through it. And so what you do is you get something here. You get a circuit that the power is independent of the data rate and the control rate. And this is fundamentally different from electronics. In other words, in electronics, what happens, you get two effects. One, you get this inductance thing. So the faster you're going, the edges, it consumes more power. That's the first thing. The second thing about electronics is you have a limited bandwidth. And so let's say you have something that's got 10 gigahertz of bandwidth, and you wanted to cover something that's 100 gigahertz. You need 10 of them in parallel. All right, so that's going to be 10 times more power. And so you get these two effects that combine that basically make electronics scale up in terms of power and in terms of size and in terms of cost with the data rate. And I wish I was could say that I was off. Well, this is what it ends up. You're going to have a situation here where optics versus electronics. Electronics, the power will go up. Optics will just stay flat. The size, electronics will go up. Optics will stay same. In fact, what happens is the loops actually get shorter. If I'm running at 10 gigahertz, I need about 30 meters of fiber to do one of these Sagnac loops. If it's 100 gigahertz, I need about 3 meters. At 1 terabit, I need a third of a meter. All right. The cost, the JDS Uniphase catalog, it costs the same. If I have a splitter, it doesn't matter what data rate I'm splitting. It costs the same. So you'll end up in a situation where the power goes down as a function of the data rate. The size goes down as a function of the data rate or the control rate. Or I call it the clock rate. And the cost will also go down this way. Now, I've been sort of pontificating about the wonders of optics for probably the last 20 years. And I will tell you the truth, this caught me by surprise. I realized this about last year. What happened about maybe 1999, sort of like at the height of the bubble, a VC firm was interested in trying to have me do something, a crossbar. And it ended up about 10% optic and 90% electronic. And I had the whole spreadsheets worked out for the cost and all this other stuff. And it just assumed that it went up like that. Then about a few years later, I had this idea of trying to do an add-drop packet ring. And that consists of about 30% optics and 70% electronics. And it ended up, the power went up at a lower slope. But big whoop, It still it's very hard to show any advantage. Well, as a lark last year ago, I plugged in basically the same components or something for an all optical state machine. And the first time when I plotted it out, it was flatline. And I said, oh, I must have broken the spreadsheet someplace. And I went back and looked at it. And I realized I had everything connected. I did it at 10, I think 100, and then 400. And in retrospect, I said, oh, yeah, that's obvious. It's constant power. All right, historical perspective. This is sort of like a little bit of shadow boxing about what I've learned, what I haven't, in trying to be a little historical here. One is this experiment. It ended up, the researcher who did it, Hercules Afromopoulos, went back to Greece, and he ended up working on this again. He pushed it like to 20 kilobits, going around for I forget how long. But after that, the experiments ended. Nobody has sort of taken this lead of trying to do a digital loop. And in retrospect, if you don't do a digital loop, you don't get to the state machines. So that was one of those things that, one perspective. The second thing was this one. Even though it seemed like crazy at the time, I said they're up to 1.28 terabits now. All right, this one down here about jitter tolerance. It ends up that if you go back to the flying saucer circuit, you'll see what happens is the signals come in here, the inputs come in here, you construct an output, and they come here and basically gate a clock signal, and the clock signal comes out and gives you a fresh edge and a fresh level, and those are used as the inputs on the next time through. And so it sort of regenerates every way through the circuit. But even then, you're going to get a little slop because there will be a little jitter in the clock. And it ends up that this is what you need to eat up the jitter. Right? And so it's really cute. It prevents, the circuit itself prevents jitter from accumulating, but this basically deals with the jitter even within the clock. Okay, the second thing has to do with the nonlinearity here. For a long time, I had sort of assumed like, oh wow, the nonlinearity, I need to keep my tops level on my levels. It turned out that wasn't the important part. The important part is the bottom part, the slow turn on. What happens if you go back to the flying saucer circuit? It is really, you don't have to worry about the ones going through the system. They sort of take care of themselves. What you worry about is the zeros going through the system and that the noise might accumulate. And I had put in ASE generators, noise generators on all the optical amplifiers, everything, And then when I did the circuit, it's like, where did the noise go? And I traced it down as the noise gets eaten really by this level. The way I found it out is I had all these fancy circuits to bias it out so that I could reduce the power that it took to turn on these gates. And when I turned on those circuits and started playing with them, the system couldn't stay stable. The stability range ended up shorter and shorter, and that was because I had basically taken out the zero suppression, the zero noise suppression. So it's kind of funny, what you think is the important feature doesn't always end up to be the important feature. All right, what turned out to be the most important things on this effort, really I would say, is the methodology by Mutant Conway. It's really remarkable that it translates directly from VLSI to optics. But it was the idea of having an API, intermediate API layer to sort of like save people from getting on each other's nerves too much. The other thing about tools, sometimes you just haven't got enough. Plumbing ain't good enough. This ends up, you have to sort of like do the plumbing and timing. And logic by itself, it wasn't enough. This is, you know, people pushed on this and it was like kind of funny, well, not funny. The Bell Labs project got canceled, the British Telecom project got canceled, and the NTT project got canceled. And the reasons are kind of interesting. The Bell Labs project got canceled mainly because it was not 2.5 gigabit. Some wise men got together and said that the customer is never going to need more than 2.5 gigabits. So we shouldn't push anything further. And when you're trying to push 100 gigabits and the manager says, well, you know, we're never going to need more than 2.5 gigabits. Well, I think now people are up to 40. This is a classic Bell Labs syndrome. You give the customer what they need and not what they want. All right? But that's, as I said, it was a Bell Labs historical problem. The British Telecom, it was kind of interesting. What happens is not only that this department got canceled, all the research got canceled. Because this is considered a wired technology. It's not wireless, the whole future. They basically, they spent so much money getting the rights to do wireless that it just completely almost gutted the rest of the company. And this one down here was NTT. Well, they had concluded that for their network, OTDM, they were going to go WDM and not OTDM. And I will show you why that was kind of a mistake later in the next few graphs. What people ask me sometimes, you know, what happens when there's no Bell Labs? I'll give you an example. What happens is this particular project ends up to be part of physics, EE, and CS. And you have to be able to sort of like hold them all in your head at the same time. The trouble is, okay, with Bell Labs, the nice thing was this was all under the same management. It was like 113. And so you couldn't bicker, and it really low, you could basically almost tunnel through these particular energy barriers. The trouble now is that's gone, and a lot of things have gone back to their traditional disciplines, like, oh, is this a EE class, or is this a CS class, or is this a physics class? And, you know, there's a gulf in between. And I just wanted to point out that various people have different tools. This was like how to analyze, this is the, you know, very fast light, how to make lasers, how to do interferometers. This one, EEs, I realized, reduced down to methodology and tools. That's what we do. We sort of like can encapsulate complexity and build it bigger and bigger. All right, CS has all these sort of recipes for how to do things. And I purposely included here the tape drive. Okay, it ends up that if you've ever read Knuth, well, I used to be fascinated by a certain part of Knuth. And it has to do with his fascination with magnetic tape algorithms. And I was just like, wow, this is the, you know, how ingenious these people are using these old things. Well, I'll tell you a strange connection. Magnetic tape, when you do a rewind, that's equivalent to a disk, and that's equivalent to a storage loop. All right? I will say no more. But a lot of these things come back, and that's why you have to learn them over again. All right. You might not have to rewind again, but, you know. Or back up. I really love that. You know, endless loop. Yeah. All right. What historical perspective? Several things are shifting here. One is you're basically the control algorithm. In other words, before it was electronics controlling optics. Here it's basically we're going to optics controlling optics. Multiplexing. It used to be WDM multiplexing, and we're literally going to time division. I'll tell you a little more why later. Switching, we're going from circuit switching to packet switching. And I'll tell you why we got sort of hung up on optical circuit switching and never went to packet switching in a second. Granularity, it ends up, people before were sort of like shoving around circuits. And this is a technology for shoving around bits. representation, I basically now view things as digital. Once you do state machine, then you can start, it isolates you from having to worry about the crap underneath, the dBs and stuff. And so you can start thinking digital and build complexity. The last one is data rate. We're going from electronic data rates to the optical data rates. All right, I want to show you, this is sort of shadow boxing, or I probably actually said some of these things at one time. It was like, now with 20/20 hindsight, what have we learned? And it's important to analyze, why did we make a mistake? Because you see all these things are true, but they're wrong. First thing is, electrons are fermions, are good for control, while photons are bosons and are good for communications. All right, it's like motherhood. How can you object to that? It ends up that in this particular gate, the photons come in here, change the index of refraction, and that affects other photons. So it's not a direct interaction. Okay? This is one of those statements. It's sort of like saying, well, everyone knows that iron sinks and wood floats, so you should make boats out of wood and not iron. I mean, it perfectly makes sense, right? Well, unfortunately, Archimedes had something to say about it. But it's just like one of those things. It was just an incorrect inference. And I was amazed at how many people would come up to me afterwards and puff up and want to give me this lecture on quantum mechanics. And what blew me away was half of them would get it wrong. They would get it reversed. But I've gotten that lecture so many damn times. All right, the next one is there's no such thing as an optical memory. It turns out there has been an optical memory. They're just closed-minded. It's an optical delay line. And the thing is, they haven't, and in fact, if you're a certain age, that's what you saw. Memory delay lines, basically capacitive delay lines, mag tape going around, there's all these amazing delay lines. And the generation just lost that. They're used to buying them in sticks now, But we have a lot of it, and you start to think about, Alan, how viable is it to do this? If you have an optical fiber, and on one channel I'm running 40 gigabits, and let's say I think it's I can get 5 kilobits per kilometer, I think. But what happened is probably 5 megabits per kilometer. But what happens is I can do 4 channels at the same time, and I can have it coming out at you at 40 gigabits each channel. And so I can really stuff it in, it's a big pipe to sort of digest. The next one, wavelength division multiplexing, is superior to time division multiplexing. Okay, this is sort of classic NTT, or a lot of people get confused. This is a religious argument. It turned into absolutely ridiculous thing. It ends up, you're only looking at a certain part of the problem. Networking consists of communications and switching. Okay, and it ends up in the communications part, WDM is simpler to do. You can do TDM, but it's a pain. But WDM said, so they said it's superior, but they're not looking at the big picture, because in terms of switching, it ends up that TDM is more important than WDM. In WDM, you can only move these big pipes of 10 gigabits around, where you really want to be able to move bits around. And that's because you're better matched. You have a finer granularity, and you're better matched to the customer. You can give 5 bits to one person, 20 bits to someone else. And so you're closer tied in. It gives you more flexibility to move around. All right? So what the people missed was, if you wanted to do the whole thing, it ends up that you have to look at both sides of the thing. All right, enough of this lecture. I can go on. I'm trying to stop myself here. Okay, optics is analog while electronics is digital. This is just ignorance. Anyone doing high-speed electronics realize that everything is really analog. It's a very thin layer there. And you just have to apply certain rules and cross your fingers, and then you'll stay digital. All right, I'm in an in an optical switch, the same photon has to come out the other end. You wouldn't believe how this has sort of led the industry off onto a little search. Now you have these flipping mirrors, you have all these other things, liquid crystals, and it's because there's this innate belief that the same photon has to come out the other end. I remember what in retrospect turned out probably to be the demise of my department. A guy named, I shouldn't mention his name. Okay, he was sort of like, he just dropped in my office at Home Dell, and he says, well, oh, Alan, I just happen to be down here. I just have a few questions for you because I've been reading your stuff. And in retrospect, I realized he was there to do judgment on me. He was the sort of the diviner of truth. And he was a physicist and real smart and a really nice guy. And he comes down to me and says, Alan, are you working on optical computing or optical switching? That was the question. And I said, I'm working on both. And he says, but you're working on an optical logic gate. That's for computing. That's not for switching. And I looked at him, I was like, what do you mean? I'll show you. And so I drew this multiplexer up, and that confused him even more. And then I actually did the truth table to show by different settings and putting the bits in, I could get those bits out the other end. He still didn't get it. And I finally realized, you want the same photon to come out the other end. And he said, yeah, but that's switching. And I said, no, I want to switch the information, not the photon. But he couldn't get that. He couldn't do that abstraction. And what ended up happening was he says, well, I don't know, I'm late, I've got to go for a meeting and all this other stuff. Well, thank you very much for your time. And I realized that was probably the end. He didn't understand it. He couldn't understand, all right? And now how many millions of dollars have been spent on the same thing, all right? You want to change the information. I pointed out to him, I said, an electronic switch, the same electron doesn't come out the other end. And that left him really confused. And he was like, he just couldn't handle that. So I'm trying to say different people have different ways of looking at things and different orientations. You don't think that you've been trained differently, but the physicists are trained differently from the EEs or trained from the CS. All right, and it affects how you look at things. There's no need to go faster in electronics since all inputs are electronic. Well, I now have any reason. It's low power. It's constant size and constant cost. In other words, they had framed the thing in such a way only for speed. And then they killed me. Okay, well, basically objected. And the answer happens to be something else. Okay? All right, now I'm done summary. Reason for doing this. It's smart. You've got logic and memory. Speed, you can go 1 terabit or more. Power is independent of clock rate. Size is independent of clock rate. And the cost is independent of clock rate. All right. I want to do something before we open up for questions. I want to dedicate this talk to my friend Scott Kenauer. He was also here at Stanford and the EE were at the same time. It turns out we never really sort of met each other in courses except for EE380. He was sort of taking it from NASA Ames and I was sort of sitting in Skilling. And we ended up working together for about 10 years. He's Mr. State Machine in terms of everything for him was state machines. And I remember arguing with him of how many bits it takes to represent the behavior of various managers we had. And I'll tell you, you're in bad shape if it goes down to 0, okay? What happened was the reason why it's Darth Vader like that, he would dress up as Darth Vader. And this happened in particular, you only used to do it around Christmas, and then it became that AT&T started wanting to exert a little more control over Bell Labs. And so we got these memos that the management should start looking a little more professional. And I remember we got copies of Dress for Success. And so basically Scott interpreted it as, well, okay, I'll dress this as my power suit. And he would show up in meetings, and there's quite something to start sitting in a meeting and having heavy breathing going on in the front row, you know. It's like he managed to dominate his own particular way, and the people didn't know what to do with him. And I think my people said, well, maybe a tie would be more appropriate. So I've actually seen Darth Vader wearing a tie. But what is important here, a few things I wanted to point out is that this slide is quite tacky, but this slide is only like 10 dB down from the tackiness that Scott could have conveyed. He has ways of being offensive, not offensive, inappropriate at many different degrees and at the same time. And that was his true feature. In fact, one of the things of why Darth is talking about surfs up, we had 2 code phrases. One code phrase was quack, quack, and the other one was surfs up. And it ended up that quack, quack meant was straighten up, they want us to act more corporate. And the other one, surfs up, was like, the stuff is getting so deep we had better think about going back to California, all right? And the funny thing about these things, these code phrases, we'd use them in line with our conversation. So all of a sudden, when we're talking to our management or something, all of a sudden you'd hear quack, quack from the other end of the room, and you know, okay, fine, you know. Or you hear surfs up, and that meant something else too. But so I thought it'd be fitting to sort of end this by sort of having Darth here or Scott. And I'm going to say it was, whenever he walked in a room, he was so inappropriate that you never had to worry about looking foolish when he was in a room. How's that for phrasing it, all right? And that was a really empowering thing in terms of it gave us a lot of freedom or a lot of breathing room intellectually. And I'm saying this for, you'll be amazed at how many people I'm going to say this for or believe in this. And it's basically, I'd like to end with the fact that, Scott, we miss you. Okay, thank you very much. Any questions? Yes?
On that multiplexer, I'm trying to understand a little more of how that works. My basic understanding of this, did you put up that slide again?
Sure.
Okay, you've got bits coming in parallel on the electronic side at some slow rate.
Yes.
And each of them goes into an optical modulator, which generates a different wavelength.
Yes.
And then you go in through this one optical gate,
Yes.
which I think you're pulsing at the output, at the desired output rate, but with a very narrow pulse, right?
Yes.
Because a 1/nth duty cycle
Yes.
or less. So now you've got all these things in parallel in different colors.
Yes.
They all go into the delay loops. Now they're still in different colors, but now they've been spaced out in time, so they slot together.
Yes.
In the series. They come together, and then somehow, I don't understand the
I
optics of
basically
this.
use this output that's in different colors to drive the gate to change the wavelength and to
okay,
reclock
so
it.
the gate input of that thing is wavelength independent.
Yes.
Okay, that's what makes it work. Thanks.
Okay, and there's another tricky point, which you pointed out. It had to do with this is reclocked. I'm using that jitter thing to reclock it up to a standard clock when I go out. Okay, so that's a trick there. And this was relatively funny. The reason why this guy's here, this is a professor of optics, Professor Lohman, and he kept on having one part of his course that the search for the hidden delta function. So in analog, there's a sort of like a Fourier transform or signal processing equivalent to this of doing this with optics. He used the delta function, and this is a standard like chirp trick that you can chirp through delay lines. But I got the front part, and it took a long time to figure out how to do the reverse. Okay, it takes a while to get your head back that way. Yeah, next. Anybody else? Yes.
HDTV is coming, so can you get us more speed? What's your speed limit?
Strange connection when you mention HT television. It ended up, Scott Kenauer was here. He did his thesis with NASA Ames on cosine compression. And it ended up that his algorithm, or a variation of his algorithm, ended up in the kernel of HD television. All right? And I remember talking about this circuit once. I said we should give it to the Japanese, so we'll put them back 5 years. He had this talent for making things, a circuit, incredibly obscure but very efficient. And so, but your question was, what does this change to HD television?
What's your speed limit? Is it some physics in the switch?
The speed limit seems to be the bandwidth of the optical amplifiers. All right? Because that's what made it free oscillate at 1.6 terabits. All right? It doesn't seem to be the switch. All right, but I'm happy at only 1.2. Okay? I'm not greedy. Yes?
I have a question about the main point you're saying about scalability not being an issue with optics.
Yes.
Whereas electronics, you know, you got this power thing. What are the concerns you are worried about, though, with optics? Don't you have to worry about, you know, the power of running the amplifier, the optical amplifier? Or, you know, are there any real scalability? Or is it like an algorithm where you're O of constant, so it doesn't matter what you scale to, so you're at some
Yeah,
point.
it ends up it's O constant. In other words, an optical amplifier, it doesn't care how you modulate the signals coming in. All right? And then a splitter doesn't really dissipate any more power no matter how your modulation is on the thing. It all has to do, trying to figure it, that it's because there's no inductance. Inductance is the killer.
Don't you have to worry about optical issues in the physics layer, like, you know, distance, like redshift, blue shift, or anything like that?
No, I can true those up. That's why I reclock every time through.
So it's
that
a
was the
form of
power.
like error correction. Those error correction feed back into the loop, so you don't have to worry about.
This is analog. I basically cut, it's an analog ways of preventing the errors and bounding them. And that's why I mentioned a few times, that jitter tolerance is important, and the nonlinearity down the bottom turned out to be important. Any other questions? Yes.
Your reclocking then handles variation and delay because of changes in the index of refraction with different wavelengths?
No, it doesn't correct for the different wavelengths. You can do that with dispersion correction. Okay, that's a constant fact. In other words, I can delay different wavelengths by different amounts. People know how to do that. That's the dispersion thing. This clocking has to do with the jitter on any oscillator. Just jitters. You know, and you have to be able to, the way you make the gate eat up that jitter is you build an extra little length in the loop so that the fast input that might come in a little late has a time to catch up and pass through the other guy. So you give it more slop, but if you add up too much slop, the guy can go through the previous bit. That's the limit. So you can eat up quite a lot of jitter that way. I haven't found any electronic equivalent that does that. And so as an electrical engineer, I was like, wow, this is cool. Yeah. Anything else? Yes?
Assuming that you move this into manufacturing, what are the issues at that layer? Because VLSI, you're just laying like metal, right? And some photos. What are we doing in the optical?
This is going to be big. You know, in other words, some of these storage loops are going to be kilometers of fibers. All right? But the nice thing is you can have, those are well characterized, and they don't take much power. Okay, a kilometer of fiber takes less light than going through a window pane. You know, it's like down to 1/10 of a dB now. So that's not the power, and you have amplifiers to boost it up. The thing I can see, there's an unknown here. In other words, this is the plumbing approach of doing it with optical fibers, just putting it together. There should exist a free space version that is completely with propagation, or, you know, and I don't know. So when you're talking about the manufacturing thing, I'll tell you right now it's a cost problem issue because it's tied to the parts that are used in the telecommunications industry. One of those wavelength splitters, the RAID waveguide gratings, you know, JDS wants $3,000 for it. Whereas people tell me they can make it under 100. And it's because they have such low quantities and the market will bear such a high price that, so it'll be a challenge of, quote, rolling our own, basically, ways of splitting the wavelengths or not. I don't know. So the cost thing, I'm not sure. We're talking still small parts or small systems right now. Yes?
What kind of equivalent gate count would you expect to be able to build in some volumetric shape?
I was amazed at how far I could get with 5 gates or 6 gates. All right? So it ends up to be really how many bits on a state machine. I don't promise you anything more than state machines at this point. All right? The state machines that I'm working on have 8 states or 16 states. It's how to compose everything down to that. I'll tell you, okay, I forgot about Scott Kenauer. He was like Mr. State Machine. And I've gotten into doing more and more of the state machine design stuff. So I feel like I'm almost channeling Scott through some of the things I'm doing. It's like McCoy and you know, Mr. Scott's, you know, in the brain and stuff like that. Or what happened is, I've done some of the state machines. It's just amazing how much you can push into a small state machine. In fact, one of them, I swear, it probably can sync up to an iPod. You know, it's like I put everything else in it. It's full duplex. It does handshakes and everything like that, and it's only done in 8 states. All right, and so, but those 8 states, I think it will be enough to handle a lot of the networking stuff, for sure. Other than that, maybe your washing machine. You know? Okay? That it?
What next?
What next is starting to get this stuff out there. What?
You going commercial?
Trying. You know, we'll see. Getting my pitch together. Right? This is my I gave a talk last Thursday to the Optical Science Center in Tucson. And together these are, and I hadn't talked for 10 years before that. So you're seeing finally all the different pieces come together after all these years. I remember you were in my living room or something and said, am I still working on this stuff? And I showed you off my coffee table some of these state machines. You know, so I'm still working on it. Yeah. Okay, that it? Thank you very much.
For information on other Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.